Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody watching us from the future. I hope you had a good resting week. We actually have not seen each other for 3 weeks because there's been 2 Fridays where we didn't have a lecture. So I'll try to reactivate a little bit the knowledge, and we'll take it from there, and then I'll continue. So we were in the middle of actually an advanced part already of the lecture, because unlike the first system that we built that is based on Boolean retrieval, we started using the power of linear algebra in order to query our documents. And in particular, we represent every document as a vector of, for example, TF-IDFs. So you might remember that TF-IDF means term frequency multiplied by inverted document frequency. Trying to find the slides where we were. And so every document is represented by a vector, and we realized that a search can be seen as looking for all the vectors that are as close as possible to the vector of the query. And by as close as possible, we mean, for example, the angle between the 2 vectors. And you know how to calculate an angle. The cosine of the angle is basically the inner product of the renormalized vectors. But now we were left with the implementation of that. How do we compute the scalar products of the document vectors and query vectors for many documents that we're interested in? And so first we need to have the number stored somewhere. And so I left you 3 weeks ago with the fact that we basically store the pre-computed term frequencies inside the postings, right? Remember, a term frequency has 2 subscripts, the term and the document. It's the number of occurrences of a term T in documents D. So we can store them here in the postings. Then we could store some form of pre-computation for the inverted document frequency for each term. And now there's only one for each term. So that would basically be the purple boxes here. But in practice, we don't store log of n over df. That would be the inverted document frequency. We just store n over df without taking the log. The reason for this, I will show you, because the IDF is not the only way you can actually model the rarity. There's other ways. And so by just taking n over df, we remain generic as for, we basically do not force the choice of the IDF over any other number, right? And then for the TF of the query, because we need the TF-IDF both for the query and for the documents, that we can do very easily because the query is very small. So that is a walk in the park to compute the term frequencies in the query. And so what's going to happen is that we are going to accumulate the scalar products. What I mean with accumulate is that a scalar product is a very large sum of products. Very large sum. And we need to accumulate that sum, right? Remember that it's a sum that is made for each document over the terms, right? So we need to traverse the entire index. So I'm putting these buckets right here that are basically going to accumulate the scalar products, right? Bucket 1 accumulates the scalar products between document 1 and the query. Buckets 2 between document 2 and the query. And initially, these buckets are at 0, and we are going to fill them with the products of the TF-IDFs. So if I take it strictly like the original version, I basically have the TF-IDF of the query times the TF-IDF of the document, right? So this is the TF-IDF of the query times that of the document, renormalized because I want the angle, right? So I have to renormalize my inner product. And basically, I have to sum that over T, the sum over T, for every D. And for every D, I'm going to put the results here. Now, how can I do that? Well, there are two strategies, because remember, it's bidimensional. We have to sum over the terms and go over the documents. So we can do it in 2 ways, right? Either we do it term at a time, meaning that I take a term and then I accumulate all documents, or document at a time, meaning that I take one document, I process all the terms, then I move on to the next documents and so on. So I'm going to show you animations for the two, but obviously it gives us the same thing, right? It doesn't matter in which order we accumulate the TF-IDFs, because that's the result is going to be the same. But you just need to be aware there's two ways of doing that. Term at a time, document at a time. So here's my animation for you. Term at a time means we start with ETH, and then we compute the TF-IDFs for document 1 and ETH, right? I get some number, it's just this basically, just for document 1 and ETH, and I add it to my bucket 1. So it used to be 0, and now I added something. Instead of putting a number, I'm just going to have some sort of bar right here that just, as we accumulate the TF-IDFs, is going to grow, right? Then I do document 2, bit smaller, document 3, document 4, document 5, document 6. Document 4 doesn't exist, so it remains at 0, right? Right? So far, so good? At that point, I've only accumulated the scores, the scalar product for just ETH, and I will also do it for the other terms. However, even though I did it only for ETH, I've already started it for all documents. Then I go to Zurich, then I'm accumulating more. Remember that it's a sum over the terms for document 3, so I have to sum this plus this, right? So I'm going to add it. I'm going to compute the TF-IDF times TF-IDF, and I add it to bucket 3. So you see it's a bit higher now. I accumulated it here. The same for document 4, which was at 0. Then we accumulate it a bit here. I'm done with Zurich. Then I go for computer, accumulate a bit for 1, for 2, 3 doesn't change, for 4, for 5, and 6 doesn't change. And now, of course, it's just a slide with very few terms and so on, but and the documents, but I'm basically done, right? So assuming my query with ETH Zurich computer, I have now accumulated my scalar products, right? This is what we call evidence accumulation. What is the document that would be returned first with this? What's the highest score? 5, yes, exactly. Document 5 would be the first to be displayed. The second one, probably document 1. 1 and 6 are actually pretty close, right? So 1 and 6. Then we'd have document 2, then 4, and then 3, right? So you see, we just sort by scalar product. But now we have the scalar products because we have accumulated, we have summed over all the terms. So that's the definition of the scalar product. What about document at a time? It's exactly the same thing, except that now I do it document by document. So document at a time, I would start with document 1, which has ETH and computer, and that's it. I'm done with document 1. Then I go for document 2, ETH and computer. Then I go for document 3, then document 4, then document 5, then document 6. Who agrees it's the same? Right? It doesn't matter in which order we do it, right? But we have a choice, term at a time or document at a time. And I did a big pedagogical mistake of not actually putting the same bars, but it's actually the same, should give the same results in here. Okay. Now, we have to sort the documents by decreasing scalar product. Right? That's the idea. That's how we find the closest. Remember that it's the cosine of the angle, right? So if the angle is close to 0, then the cosine is close to 1, right? So if I sort by increasing angle, then I sort by decreasing scalar product. Now, if we sort, what is the complexity, the optimal complexity for sorting a list? That should be automatic all at the same time. What is the complexity for sorting? N log n, exactly, that you know, right? You've heard it many times. So you might think, okay, maybe we need n log n. But think about the UI, the user interface for that engine. Do you think we're throwing directly all the documents at the users? Is that what Google does? They don't do that. They give you the first 10 pages, the first 10 results. Then you need to click to get the next 10 results. So it means that we don't need to sort everything. We just need to locate the top 10 scalar products. What do you think is the complexity for that? Who thinks it's also n log n? Who thinks it's O of n? O of log n? So it's O of n. The majority is correct. And for this, we actually use a priority queue or a heap that basically is able to do that for us. So building the priority queue takes linear time. And then unqueuing, every time you unqueue something takes log n. But since we only unqueue the top 10, we basically have 10 times log n, right? So we basically have O of n plus 10 times log n, so it's still O of n, right? How would I get the n log n? That's if I unqueue everything, then I have n times log n, right? But I would have to unqueue everything to have n log n, right? If I unqueue a constant number of documents, I'm still at O of n globally. And the O of n comes from the construction of the queue. Who is with me? Right? So it's good to understand the complexity of this, that it's in linear time. Now, to finish this section on vector space model, I told you that the TF-IDF is the most common scheme that people use. It's the one that is used in almost all textbooks, but it's not the only one. In fact, there is some sort of restaurant menu from which you can pick and build your own weights for your vectors. And this restaurant menu has even codes to say what you want to do. For example, n, I'm putting it in parentheses, n is the code to say that you're using the term frequency, right? So the weight is on the y-axis, the term frequency is on the x-axis. If you take the term frequency as the weight, then it's y equals x, right? That's just the identity function. The weight is the term frequency. That is code n, if you do that. Some people do not want to do that. Instead, they prefer to take a bit of a log and kind of not have too high weights when the term frequency increases. So they are going to take 1 plus the log of the term frequency, right? It's just a slight variation. So it means that instead of having the TF-IDF, you have the 1 plus log TF-IDF, right? Then you just have different numbers in your vectors. If you want this, you use the code L instead of N, right? So this is N, this is L. It's called sublinear term frequency scaling. Then you have augmented term frequency scaling. So what it does here is that it doesn't just take the log, it actually kind of rotates the curve. So it was like this, and it rotates it like this. What this actually does, the explanation for that has to do with smoothing. Because the terms that never appear, if you have too small a sample of the collection, they might be underestimated because because of the sample, you didn't see them a lot. And tilting like this, the curve a little bit is going to smooth a little bit the numbers. So it has to do with statistics, right? But anyway, it's just yet another formula. So some people are going to use A plus 1 over A TF divided by TF max. It's just some formula. You don't need to know it by heart. Don't worry. But it just does this tilting, right? And so the people who want to use this instead of the others, they use code A, right? So you have N, L, A, for example, for the term frequencies, right? It's just something you plug into the computation of the weights when you compute them. There are some people who don't even want to make a difference. They basically don't want bags, they want sets of terms. So either a term is in the document or it's not in the document, just like the Boolean querying. In that case, the weight, the TF, is going to be just 1 or 0, right? They take 1 if the TF is positive, and they take 0 otherwise, right? So basically, that means that instead of the TF-IDF, you're basically going to have 0 if the term doesn't appear, or just IDF if the term appears, right? For whom is that clear? Right? So these are 4 ways that we can proceed with. TF is the first one, but there's 3 other ways in there. Oh, actually, yet another one. Don't be scared by the formulas. You don't need to learn them by heart. I'm just telling you there's plenty of other ways to do that, right? Here they just take yet another way of doing that. Okay. So these are all the possibilities that you have for the term frequency, and you have a code, N, L, A, and so on for the term frequency. in exactly the same way, you can also change the IDF and put something else than the IDF instead. Some people don't even want an IDF at all. They just want the TFs. They don't just want the term frequencies. In that case, they just take, for the document frequency, they just take 1. They just multiply by 1, and that's it. Right? So they would just have vectors of TFs, if you take the TF, of course, on the other side. Then there is, of course, the IDF. So this one you know, right? That's the IDF. Who recognizes the IDF here? That's the inverted document frequency, right? Log of n divided by the document frequency. Who recognizes this? You do, right? I showed it. Okay, very good. So that's code T, right? So that's code N for the document frequency absent, no document frequency. T for the inverted document frequency. There is another one with, it's incredible, the fancy formulas that people come up with. So this one is yet another modification of the log of n over df, just slightly tweaked. Now you might wonder why. We'll know in a couple of weeks, because I'll introduce you to probabilistic information retrieval. It turns out that when you do probabilistic information retrieval, you obtain a formula that looks more like this. So this is the reason why some people prefer this instead of the inverted document frequency. That's code P, right? So we have N, we have T, we have P. So that's for the inverted document frequency. So you can tweak the term frequency. You can tweak the document frequency, inverted document frequency. And there is a third thing you can tweak. It's the renormalization. Because in the standard approach, I told you, you just renormalize with the Euclidean distance, right? That works, that's the default. But there's other ways. First, there are people who don't even want to renormalize at all. They just put the TF-IDFs, they don't even renormalize to 1, right? So that's code N for the normalization, no normalization. Then there are people who use the cosine normalization, so the Euclidean distance to the origin. That's called the cosine normalization, and that's code C, right? That is the standard one. That is the one that we've used until now. And there are other people who like to use instead the size of the document, the number of characters in the documents to renormalize for some reasons, right? That's code B for the people who want to do that, right? And then there are people who want to tilt the curve and do the same kind of tilted as they did with the term frequency, and they have yet another super scary formula right here that is tilting the normalization. That's code P, right? But basically, what I want to say here, you obviously do not need to know all these formulas by heart. You at least need to know the one with the term frequency activated and the one when it's just Boolean. For the inverted document frequency, you need to know the code for none at all and for the IDF. And for the normalization, you at least need to know the code for no normalization at all and the cosine normalization, right? And you don't need to know the other formulas or anything. But basically, these codes are used like this. When you have an information retrieval system that you want to configure, you're basically going to give 6 letters. The first 3 letters indicate the convention you picked for the documents. So for the document weights, you pick a code for the term frequency, a code for the document frequency, and a code for the renormalization. And the same for the query rate. You take a code for the term frequency for the query, a code for the document frequency, and a code for the normalization of the query. Normally, if I did my job correctly, you should now be able, based on all the slides, not learning by heart, but seeing the slides, if I give you these 6 letters, any combination, you should be able to compute all of the weights of the vectors. Who would be able to do that? Right? Very good, most of you. You just need to look up these codes. The first one, term frequency, second one, documents frequency, third one, normalization, and you just look up the formulas and apply the formulas, right? The standard one, again, is the term frequency, the IDF, and the cosine normalization. That is the standard one. All right. And this is where it stops for this one. By the way, this is called SMART. SMART is the name of the system. It's already a few decades old now. That was one of the early systems for information retrieval that were conceived. And so this notation here is still in use today by some of the systems. Okay, and so in the exam and in the exercises, when we use these exotic things here, we tell you, we remind you, okay, that's the code for this, that's the code for that. Again, you just need to know the standard ones, right? So as I said. Very good. Any questions so far? No questions in the lecture hall on Zoom. Any questions? Last chance? No questions? Okay. Well, you can still ask questions later, right? So also on the forum. So let me move on. So stop the recording.